Hello everyone. So again with the next topic, we have already discussed about the definition of the drift velocity, right? So today we will derive the expression for drift velocity, right? So for deriving this, we are considering a piece of a conductor. So this drift velocity. We are considering a piece of a conductor, say suppose a wire, right, of uniform cross-sectional area A, and the length of this piece of wire is suppose L, right? And let's say suppose we know that it has free electrons. This is a conductor, that's why. So small n is the number density of electrons. What does that mean? Number of electrons per unit volume. Per unit volume. Right? So here, let's first recall what is meant by drift velocity. So drift velocity is the average velocity attained by the electrons in a direction opposite to the applied electric field. Right? So we remember this definition. So this is the average velocity attained by the electrons in a conductor in a direction opposite to the applied electric field. Right? Now for this, we know that when electric field is not applied, the free electrons are randomly moving in all the directions. So when no electric field is there, then what will happen? The electrons will randomly collide with one another and the ions, right? And they will move along different directions. Though the velocity during these collisions will change because there will be a change in direction, but the magnitude will not change, right? So if these electrons are randomly moving in all the directions, then net velocity before the application of electric field will be 0. So you can say that if U1 is the initial velocity of one electron, U2 is the initial velocity of second electron, and so on. U3 is the initial velocity of third electron, and so on. Un is the of nth electron. Right? So you can say that if the total number of electrons is capital N, so the average velocity without application of electric field, so you can say that initial average velocity that can be written as U1 plus U2 plus up to Un upon number of electrons. So this will be 0. Why it will be 0? Because the electrons are randomly moving in all directions. Right? In absence of electric field. Right? So this is the net average velocity is 0. Net average initial velocity is 0 in the absence of electric field. What if the electric field is applied now? Let's consider this case if the electric field is applied now. right? So again, we are considering the same conductor of the same area of cross section, same length, same number, density, right? Now we have applied an electric field in this direction, right? The electrons are still colliding with one another, right? But due to the effect of this electric field, these will experience some drift along a direction opposite to the electric field. So the electrons will gain some net velocity in a direction opposite to the electric field. So if I write the expression which relates final velocity and initial velocity, I need to consider the time. What is this time over here? We know that these electrons are colliding, right? So the time between successive collisions is called as relaxation time, right? So if I am writing this expression relating the final velocity of first electron and initial velocity of first electron plus acceleration of first electron into relaxation time of first electron. So what is relaxation time? Where T1 is relaxation time. What is this relaxation time? Time between successive collisions, right? Similarly, I can write the other expressions for other electrons also, but we need to check what would be the value of this acceleration for these electrons. So I need this space. I am rubbing this part of the board and just calculate. So these are all clear. So I am just rubbing up to here. And I can say that if V1 is equal to U1 plus AT1. So we know that here force is mass into acceleration. This is one formula which is by Newton's second law. And second formula over here will be by electricity force. This will be charge on an electron into electric field, right? So this will be the formula for force. If we equate these two, so I can write this as first equation, this as second equation. So from 1 and 2, right? Ma is equal to minus EE. So from here, the acceleration is minus EE upon m, right? If I am writing all this in vector form, I can simply write this thing, right? So this is the formula for acceleration. I am marking this as equation 3, right? So here, I'll just shift this line over here so that I can get a continuity over here. So we know, we have already written that V1 is equal to U1 plus A T1, where T1 is the relaxation time for first electron. Right? Acceleration will be same for all the electrons because we know that the electric field applied is same, charge on electron is same, mass of the electron is same. So A will be same for all the electrons. Now I can write for second. So I will get this V2 is equal to U2 plus A T2. Similarly, I can write for all the electrons, and for nth electron I can write UN plus ATN. Right? If I these, right? So adding these, I'll get all these equations of velocity. What will I get? V1 plus V2 plus dash 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 plus Vn on left side, right? And on right side U1 plus U2 plus up to Un plus A common and T1 plus T2 plus up to nth relaxation time, right? If I divide the whole equation by capital N, where N is equal to number of electrons. So if I divide the whole equation by N, what will I get, beta? I'll get V1 plus V2 plus Vn upon N is equal to U1 plus U2 plus Un upon capital N plus A common, and here T1 plus T2 plus Tn upon N. So what will it be? This is the average final velocity attained by electrons in presence of electric field. So this I can replace by drift velocity, right? This is the average initial velocity, which we have already discussed is 0 due to random motion in absence of electric field, plus A over here, and this is the average relaxation time, which I can replace by tau, right? So this step is clear. Up to this step is clear. Now I am rubbing the board for the next step, right? So after this, what will I do? I will use this equation 3, right? And will get the final result. So I can mention here that where tau is the average relaxation time. And what is relaxation time? Relaxation time is the time between successive collisions. So average relaxation time is the average of these relaxation times. So from third, and I'm marking this as equation 4. So the last step I'm writing here after rubbing these two steps. This is the last step of this derivation. From third and fourth, what will I get? This is the average velocity attained by electrons in presence of electric field in the direction opposite to electric field. This is equal to, for isolation I am writing, minus E upon M into tau. So this gives us the formula for the drift velocity. If I want to write just the magnitude, I can write just the magnitude like this, that Vt magnitude is E tau upon M. I hope this is clear to everyone, right? Now we will derive a relation between drift velocity and current, right? So I'm rubbing this part and then I'm moving on to the next topic, that is drift velocity and current relation. I'll need these things over here. I'll need this diagram with presence of electric fields. I'm not rubbing this. I'm simply writing the heading, relation between current For this relation, I'll use the basic formulas which you already know. What am I doing is current and drift velocity. So I know the formula for current, right? So I is Q upon T, right? Rate of flow of charge is current. So from here, we know that what is Q? Q is capital N into electronic charge upon T, right? So we know that capital N is number of electrons. If small n is the number density of electrons, so I can say that small n is what? Capital N upon volume, right? Capital N is as it is. If I want to write this volume for this, so here volume is A into L. We know that base into height will give the volume of this cylindrical piece of wire. So this is A into L. So we know that small n is N upon AL. So therefore capital N is what? Small n into AL, right? So let's mark this as equation 1 and this as equation 2. So from 1 and 2, I can replace this capital N. So I'll get I is equal to small n into A into L for capital N. And I'm writing E over here and T as it is, right? Now if you look at the diagram for the conductor, this is length of the conductor. So this is the distance moved by the electrons. So distance upon time, this part is what? It's velocity. And this distance is moved by the electrons due to drift velocity. So I can write this like this, N into A. Replacing this term, I'll get this into E. And D must be smaller because D is the suffix which is used here to denote drift velocity, right? So this gives us N, E, A, V and V suffix, right? So the current is N, E, A, V. So this is the relation between the current and the drift velocity, right? That's all for now. Thank you and have a nice day.